Imagine steering a car while the road constantly moves beneath your wheels, not just forward, but side to side, up and down, all while you are trying to hit a target that is also dodging unpredictably. Now make the car a warship. Make the target another warship 7 miles away. Make your projectile a shell that takes 30 seconds to arrive. By the time your math says fire here, both ships have moved. The shell splashes harmlessly into empty ocean. This was naval warfare in 1914. It was mathematically impossible in real time. Gunners could calculate where to aim, but the calculation took longer than the answer stayed valid. What if, instead of calculating and then acting, you built a machine that never stopped calculating? What if the equations kept running continuously while the battle raged? How do you make metal think faster than humans under fire? The North Atlantic, 1914. Naval engagements were stretching beyond 10,000 yards, nearly 6 miles of open ocean between warships. Battleships and cruisers could hurl shells across those distances, their guns capable of throwing a ton of steel through the air, but hitting anything required solving a vicious equation with constantly changing variables. Your ship's speed and bearing, the enemy's speed and bearing, wind velocity at multiple altitudes, shell time of flight, which itself varied with range, temperature, and barrel wear. Each factor shifted moment by moment. Gunners relied on printed firing tables, thick books of pre-calculated solutions for static scenarios. A range officer would estimate the enemy's course, flip through pages of logarithmic tables, call out an angle, and the gun crew would manually aim the turret. By the time they fired, everything had changed. The shell landed where the target used to be, not where it was going. Think about the frustration. You have the range, you have the weapon capable of striking across miles, but the mathematics defeats you. Human calculators, even working frantically with slide rules and mechanical adding machines, could not integrate changing inputs fast enough. The problem was not the gunner's aim, it was that the answer expired before you could use it. Why could not trained gunners just aim better? Because mathematics moves faster than human muscle, and modern warships move faster than manual arithmetic could track. By 1915, both British and German fleets had recognized the crisis deepening with every naval engagement. Artillery officers watched their hit rates plummet as engagement speeds increased and ranges extended. The faster ships became, the worse the problem grew. Mathematicians brought in to study the issue explained it in stark terms. Effective fire control required continuous integration of differential equations, the mathematics of constantly changing rates. You were not solving for one static moment in time, you were solving for the precise intersection of two moving trajectories 30 seconds into the future, with both trajectories themselves changing unpredictably as captains maneuvered. Static calculations handled fixed variables perfectly well. Naval combat had no fixed variables. Every second of delay between calculation and firing meant the solution drifted further from reality. The equations went stale almost instantly. Plotting boards helped. Large tables where officers manually tracked ship positions with grease pencils and rulers, updating graphs of relative motion, but they could not keep pace with the chaos of battle. Picture an officer frantically updating a hand-drawn graph while shells explode around his plotting room, trying to predict where an enemy ship will be in half a minute based on where it was 10 seconds ago, all while his own ship is turning and accelerating. How fast does math need to be? Faster than the ships themselves, faster than human hands can move rulers across paper. Continuous, like the motion it is trying to predict. The U.S. Navy, preparing to enter the war in 1916, evaluated the problem with systematic American engineering pragmatism. The Bureau of Ordnance in Washington tested every available mechanical aid, improved slide rules with specialized scales for ballistic calculations, spherical trigonometry devices that mechanized certain angular conversions, and increasingly sophisticated plotting boards with pre-printed trajectory curves. Each tool helped with part of the problem. Slide rules accelerated individual calculations, reducing a 5-minute computation to 30 seconds. Plotting boards visualized relative motion clearly, making maneuver patterns obvious. But none of these devices could integrate changing inputs in real time. They were still fundamentally tools for human calculators, not replacements for human thought. Think carefully about what real-time mathematics actually requires. You need to continuously add your ship's velocity vector to the target's velocity vector, account for wind effects that vary with altitude, calculate shell trajectory based on current range and bearing, and output a continuously updated firing solution, all while every single one of those inputs is changing second by second. An officer with even the best slide rule still calculates in discrete steps, measure the current conditions, compute based on those conditions, output a firing solution, then repeat the entire process. The gap between those steps, even if it is only 15 seconds, is where accuracy dies and shells miss. What would true real-time mathematics demand? A calculating device that never stops running, one where the output updates continuously and instantly as the inputs change, where physical motion itself performs the mathematics without any calculation steps at all. Enter Hannibal C. Ford, a New York precision engineer who had spent years designing delicate mechanical instruments for ships and submarines. Ford ran the Ford Instrument Company, a small but respected firm that specialized in navigation equipment, optical rangefinders, and ship's chronometers, devices where precision meant everything. By 1916, he had become obsessed with what seemed like an impossible idea. What if you did not calculate trajectories at all? What if, instead of using mechanisms to help humans calculate, you built mechanisms where the rotating shafts and intermeshing gears themselves represented the mathematical equations, and the continuous mechanical motion of those parts directly generated the answer without any calculation step? Think of it this way. Imagine a gear spinning at a rate exactly proportional to your ship's speed. For example, 1 revolution per knot. Another gear represents target speed, spinning at its own rate. Connect them through a differential, a clever device borrowed from automobile transmissions that adds or subtracts rotational motion, and suddenly the output shaft's rotation rate automatically equals the relative velocity between the two ships. No calculation, no delay, no human intermediary. The machine physically embodies the equation. The motion is the mathematics. Can physical motion itself calculate? Ford believed it not only could, but must, not through computational shortcuts or clever approximations, but through continuous mechanical integration, the machine performing calculus through the pure physics of rotating parts. He was not proposing to build a better calculator, he was proposing to build a computer that thought in motion. Ford's workshops in Lower Manhattan in 1917 became laboratories for a new form of computation. The core concept was mechanizing calculus itself, making the mathematics physical. In mathematical terms, integration sums continuous change over time. A rotating shaft's angular position integrates its velocity. The shaft remembers how fast it has been spinning and for how long. Ford proposed linking multiple shafts through carefully designed gears, differentials, and cams, with each shaft representing a variable in the fire control equations. Ship speed would drive one shaft's rotation rate. Target bearing would drive another. A differential would combine them mechanically. The output would drive a third shaft that directly positioned the gun, with no human intervention between input and action. What if the equations never stopped running? The mechanism would not compute a firing solution in the traditional sense. It would be the firing solution, continuously updated every fraction of a second. Machinists and naval consultants crowded around Ford's prototype benches, watching experimental assemblies of brass gears and steel shafts spin and mesh. Turning rotational angles into mathematical values was not conceptually new. Ship steering wheels had used gears for decades to translate rotation into rudder position, but this was profoundly different. This was not gears merely transmitting motion. This was gears performing arithmetic, then performing calculus on the results, then outputting direct physical action. Metal doing mathematics through motion alone with the precision required to hit targets 6 miles away. The mechanism breakdown reveals the true genius of the design. Differentials, the same elegant devices used in automobile transmissions to let wheels spin at different speeds while turning, could add or subtract rotational speeds with perfect mechanical precision. Feed 2 input shafts into a differential gear assembly, and the output shaft spins at their sum or difference. that is addition and subtraction through pure mechanics, with no calculation required. Cams, precisely machined surfaces that convert rotation into linear motion, could embody any mathematical relationship. A spiral cam turns constant rotation into linearly accelerating displacement, mechanically performing differentiation. A logarithmic cam converts multiplication into addition. Ford stacked these components into calculating chains of remarkable sophistication. Shaft A, mechanically driven by the ship's pentameter log, spins at a rate proportional to knots per hour. Shaft B, connected through electrical synchros to the optical rangefinder's target-bearing scope, spins at the angular rate the target is moving across the horizon. Differential C combines them through its planetary gears, with the output shaft spinning at a rate representing relative velocity. Cam D, machined with a logarithmic spiral, converts that relative velocity into shell time of flight. Differential E factors in wind velocity from anemometer inputs. The final output shaft, through a servo amplifier, drives the gun mount's electric motor directly. Inputs become outputs continuously, mechanically, with absolutely no calculate, then act gap. But can metal actually handle the mathematical precision this requires? That was the brutal engineering question. Gears have backlash, microscopic gaps between teeth. Shafts flex under torque. Bearings have friction. Mechanical error accumulates with every gear mesh. Testing rigs throughout 1917 pushed precision mechanical engineering to its absolute limits. Ford's team obsessed over backlash reduction, eventually developing spring-loaded anti-backlash gears where opposing springs kept teeth constantly pressed together from both sides, eliminating the microscopic gaps that caused error. They painstakingly balanced torques across entire shaft assemblies, so no single component bore excessive load that would cause flexing. Most ingeniously, they introduced oil damping, using precisely calibrated thick lubricants that smoothed out oscillations and vibrations and prevented errors from compounding into chaos through mechanical resonance. Think carefully about the forces and the level of precision involved. You are calculating firing solutions for naval guns that recoil with literally tons of force, mounted on ships that roll and pitch in heavy seas, with all this force transmitted through slender shafts spinning at varying speeds, and you need the final answer accurate to fractions of a degree. Navy observers assigned to Ford's workshops watched test assemblies run continuously for hours, meticulously measuring angular drift with precision optical instruments. 1/10 of a degree of error at the gun breech translated to hundreds of yards of miss at a range of 10,000 yards. How precise is precise enough for mechanical computation? Precise enough that the unavoidable mechanical error remains smaller than the inherent dispersion of naval artillery itself, the natural spread of shells even when aimed identically. Ford's computers achieved exactly that, mechanical accuracy within 1/4 of a degree, sustained over minutes of continuous operation. The metal could think precisely enough. The finalized 1918 design was officially christened the Mark I Fire Control Computer by the Navy. Ford's production team and the sailors who operated it simply called it the Range Keeper. It kept the range solution alive and current. Picture the physical device, a steel cabinet approximately 6 feet tall and 4 feet wide, weighing nearly a ton, packed with hundreds of precision gears, multiple differential assemblies, carefully machined cams, and interconnected shafts, all turning in orchestrated mechanical harmony. Inputs entered through multiple channels. Handwheels allowed manual input for estimated values. Electrical synchro transmitters, ingenious devices that converted remote shaft rotations into electrical signals, which were transmitted over wires and converted back to mechanical rotation at the computer, brought in real-time measurements. Ship speed, measured by a pentameter log trailing behind the hull, drove input shaft 1. Target range, measured continuously by stereoscopic optical rangefinders mounted high on the ship's superstructure, drove shaft 2. Target bearing angle, tracked by directors slewing to follow the enemy, drove shaft 3. Target speed, estimated by measuring how quickly the range was closing or opening over time, drove shaft 4. Inside the cabinet, invisible to operators, the mechanical ballet performed continuous integration. gears meshed, differentials summed motions, cams translated rotation into calculated corrections. The output emerged as constantly updated gun elevation and traverse angles, transmitted electrically to the gun mounts themselves. Servo motors, powerful motor-driven actuators, receiving electrical signals, physically moved the massive gun barrels to follow the computer's commands. What happens when guns follow mathematics continuously? They hit targets that manual gunners miss. Live fire trials off the Atlantic coast in early 1918 proved the concept with startling, undeniable clarity. Test officers from the Bureau of Ordnance ran systematic comparative shoots, pitting conventional manual plotting methods against range-keeper-assisted continuous fire control. Gunners using manual methods, skilled range officers with years of experience working with the best available plotting boards and slide rules, achieved roughly 3% hit rates at maximum effective range. 1 shell in 30 found the target. The same gun crews, same conditions, same target ships equipped with range keepers jumped immediately to 12% hit rates, 1 shell in 8. Think carefully about what that fourfold improvement actually means in combat. It is not just more hits on paper, it is engagements resolved in half the time, reduced ammunition expenditure, meaning longer patrol endurance, and crucially, tactical advantage. Your guns reach maximum effectiveness at ranges where enemy ships still struggle with the impossibility of manual calculations. The trials documented another breakthrough that changed naval tactics: engagement time from target acquisition to first accurate salvo. Manual plotting required 3 to 5 minutes to generate initial firing solutions, an eternity in combat. The rangekeeper output valid firing solutions within 30 seconds of receiving initial target data, then updated continuously, instantly adapting as ships maneuvered. Does this fundamentally change naval combat? Absolutely. Speed transforms from a limitation that makes firing harder into an asset you can exploit. Longer ranges become tactically practical instead of theoretical maximums. Naval gunnery transforms from an experienced art practiced by skilled range officers into systematic fire control, executed by machines and supervised by humans. Atlantic deployments in late 1918 saw rangekeepers installed on U.S. destroyers and cruisers joining the convoy protection war against German U-boats. Combat action reports, declassified decades later, confirmed what controlled trials had suggested. Mechanical fire control enabled tactical capabilities previously considered impossible. Destroyers engaged surfaced U-boats at ranges exceeding 8,000 yards, distances where manual plotting had been pure guesswork, little better than firing blindly and hoping. Hit rates against maneuvering surface targets climbed dramatically. Ammunition efficiency improved proportionally, with fewer shells wasted on misses. Faster engagement from detection to accurate fire meant submarines had less time to crash dive to safety. Fewer shells required per hit meant ships' magazines lasted longer, directly extending patrol endurance between refueling stops. What else can this mechanical computation enable? The question rippled through naval engineering bureaus in Newport and Washington. If mechanical analog computers could solve the continuous differential equations of surface fire control, what about anti-aircraft fire prediction, where targets moved in 3 dimensions at higher speeds? What about torpedo deflection calculations for submarine attacks, where the torpedo itself was a moving weapon aimed at a moving target? What about submarine approach problems, calculating intercept courses? The rangekeeper was not just solving one specific tactical equation, it was proving a fundamental principle about computation itself. Continuous analog computation could handle any problem describable in differential equations. The machine was not merely a calculator in the traditional sense, it was a true computer, a device that computes continuously in real time as conditions change. Post-war analysis and technical conferences in 1919 crystallized the breakthrough's broader significance. Engineers and military analysts recognized they had crossed a fundamental threshold in human-machine collaboration. Before the rangekeeper, humans computed solutions and machines executed human commands. After it, machines computed solutions and executed them while humans supervised and provided strategic direction. One solved problem, hitting moving targets from moving platforms, had unlocked the concept of system automation. Anti-aircraft fire control needed exactly the same continuous calculation architecture. Target velocity in 3 dimensions, shell ballistics, constantly changing lead angles, all shifted faster than any human could manually track. Ford Instrument Company immediately began developing anti-aircraft computers using identical mechanical principles. Torpedo fire control for submarines used the same fundamental architecture, with differentials integrating relative motion. Bomb sight stabilization for aircraft relied on mechanical integration to compute ground speed from airspeed and wind. Is this actually a computer? The question energized engineering departments at universities. Some conservative voices argued that true computers required universal programmability, and that these were merely special-purpose mechanical calculators. Others countered forcefully that computation is computation regardless of implementation, and that continuous solution of differential equations through mechanical embodiment absolutely counted as computing. Today, retrospective definition sides decisively with Ford and his defenders. The Rangekeeper was an analog computer in every meaningful sense, and the first such computer successfully deployed for real-time tactical control in combat conditions. Mechanical, continuous, and devastatingly effective. Through the 1920s and the 1930s, Ford Instrument Company and emerging competitors refined the architecture relentlessly, generation after generation, improved differential assemblies with even tighter manufacturing tolerances, reduced backlash to near zero. Feedback loops corrected for accumulated mechanical drift by comparing predicted impact points with actual shell splashes observed by spotters, then adjusting internal mechanical calibrations to minimize future error. Self-tuning mechanisms adapted to individual ships' unique characteristics, each vessel's actual speed versus indicated speed, and each gun's particular ballistic properties. The Mark I evolved into Mark 1A, then Mark 1B, then Mark 1C, each generation faster, more accurate, and more reliable. By the mid-1930s, the evolutionary lineage had produced the Mark 1A Rangekeeper, which became standard equipment on United States Navy battleships and heavy cruisers. Thousands of units were manufactured. Where does analog computing go from this foundation? Directly into aviation. The legendary Norden bombsight, famous for enabling precision daylight bombing, used nearly identical mechanical integration principles to continuously solve the ballistic equation for bombs falling from moving aircraft. Coastal artillery benefited as mechanical computers calculated firing data for massive shore defense guns protecting harbors. Aerospace guidance adopted the same ideas as autopilots, stabilized aircraft using continuous feedback computation of control surface positions. Ford's central principle, physical motion embodying mathematical equations, became the foundational architecture for an entire generation of control systems across military and civilian applications. World War II proved the Rangekeeper's ultimate vindication and drove its final evolution. Updated Mark 1A and Mark 8 Rangekeepers directed the guns of every U.S. battleship and cruiser throughout the Pacific Campaign. At the Battle of Surigao Strait in 1944, the last battleship engagement in history, American fire control computers enabled devastating accuracy at night against Japanese forces. Battleships scored hits at ranges exceeding 20,000 yards in darkness, a feat absolutely impossible with manual methods. The mechanical computers had become so reliable, so trusted, that gun crews followed their outputs without question. After the war, detailed analysis showed that Rangekeeper-equipped ships achieved hit rates approximately 8 times higher than comparable World War I vessels using manual fire control. 8 times. That's not incremental improvement, that's a revolution in capability. But even as analog mechanical computers reached their peak of development and deployment, their obsolescence was approaching. The ENIAC computer, demonstrated in 1946, could perform calculations thousands of times faster than any mechanical system. Digital electronic computers did not need gears or differentials. They did not accumulate mechanical error. They could be reprogrammed for different problems. By the 1970s, digital fire control systems replaced mechanical rangekeepers throughout the fleet. The last mechanical fire control computers were removed from active service in the early 1980s. The age of mechanical computation ended not because it failed, but because something faster came along. Modern engineers and historians study the rangekeeper as foundational technology that bridged two eras of computation. Aviation still relies on principles Ford pioneered: inertial navigation systems, mechanically integrate acceleration into velocity and position, direct descendants of Ford's differential calculators even when implemented electronically. Flight control computers, even modern digital ones, implement control laws originally developed for analog mechanical systems. Simulators teaching pilots and gunners still sometimes use analog computation for certain real-time physics. Hydraulic motion platforms integrate acceleration inputs into realistic g-forces using mechanical principles unchanged since 1918. Engineering historians recognize the rangekeeper lineage as the crucial bridge between human calculation and digital electronic computing. It proved that machines could think continuously in real time under the chaos and violence of combat. It demonstrated that computation could be automated, that humans could supervise rather than perform calculation. The same fundamental principles, miniaturized and translated into electronics, run invisibly in vehicles and aircraft today. Anti-lock braking systems continuously integrate wheel speed and compute brake pressure, analog logic in digital form. Fly-by-wire controls in modern aircraft compute control surface positions hundreds of times per second. Stability control in cars calculates correction angles faster than any human could react. The architecture persists: continuous sensing, continuous computation, continuous action. Ford's vision of machines that think through motion became the template for how we still build control systems a century later. The gearbox is still there, in a sense, not literally. Digital processors replaced mechanical differentials and cams decades ago, but the foundational principle persists, embedded in every control system around us. Continuous integration, real-time computation, inputs becoming outputs without delay, without steps, without calculation gaps. Every autopilot in every aircraft continuously integrates motion data from gyroscopes and accelerometers, computing corrections exactly as Ford's mechanisms did. Every flight control system computes aerodynamic forces as they change moment by moment. Every stability control system in modern automobiles calculates correction angles thousands of times per second. Every industrial robot continuously solves the differential equations of motion to move smoothly. We stop noticing because it works perfectly, invisibly. That's Hannibal Ford's legacy: engineering so elegant, so fundamentally correct, that it becomes invisible infrastructure. The machine that taught metal to think faster than humans didn't just win naval battles in 1918. It taught us that computation could be continuous rather than discrete, embedded directly into control systems rather than separated from action, automated rather than manual. It proved that machines could be trusted with decisions in real time. When you feel anti-lock brakes pulse under your foot, when an aircraft autopilot holds altitude precisely, when any machine responds smoothly to changing conditions, that's Ford's principle still working. That's when engineering becomes perfect, when it disappears into capability we take for granted.